Hello, this is Ms. DB, and in today's lesson we are going to look at multiple representations of functions like tables, graphs, equations. We will translate between those various representations of functions and solve problems by using some of the characteristics of each of those. Here's an example. We have an amusement park manager estimates daily profits by multiplying the number of tickets sold by 20. The verbal description is one way you can describe a function, and that's useful, but other representations of functions might be more useful. We can write an equation. We can say profit equals 20 times n, where n is the number of tickets. Or in function notation, that would be p of n equals 20 times n. We could make a table showing some different values of n and what you would get for the profit. So 50 times 20 is 1,000, and so on. We could make a graph, which is very helpful. These different representations can help the manager set, compare, and predict prices. Here's a business application, and it says sketch a possible graph to represent the following. Ticket sales were good until a massive power outage happened on Saturday that was not repaired until late Sunday. So ticket sales were good, so they're going to increase, and then on Sunday or on Saturday the ticket sales went down because there was a power outage. So this is showing that on Friday they were very good sales, and then it decreased because there was a power outage that was not fixed until Sunday, and then you can see that it increased again. That's one possible graph. Here's another possible graph for the weather was beautiful on Friday and Saturday, but it rained all day Sunday and Monday. Same problem with the ticket sales. So beautiful on Friday and Saturday, so good sales, but then the sales went way down because it rained all day Sunday and Monday. And how about this one? Only half of the rides were running on Friday and Sunday. So on Friday and Sunday there was less ticket sales because there wasn't as many rides, so people didn't want to go. So Friday it was low, Saturday was high because all the rides were working, Sunday was low, Monday was back up again. So this is just a possible graph. We aren't using actual data, we're just saying this graph could match this verbal description. Because each representation of a function, words, equations, tables, or graph, describes the same relationship, you can often use any of those to generate the others. So we were using verbal to make a graph, but we can do more than that, especially if we have actual data. Like in this case, Janet is rowing across an 80-meter wide river at a rate of 3 meters per second. So we know how wide the river is, we know how fast she's going. Create a table, an equation, and a graph of the distance that Janet has remaining before she reaches the other side. So we're starting with the 80, and then her time at 0 is still 80. But then after every second, it's going to go down, subtract 3, because she's going 3 meters per second. So the time after 0, 1, 2, 3, 4 seconds are given here. Now this wouldn't be the whole table because she doesn't end up at 0 yet. The distance decreases by 3 each second. The equation might be a little better for this one. The distance is equal to 80 minus 3 meters per second. So we could write that as d equals 80 minus 3t, where t is the time. And then we could also graph this. We know that the total distance is 80, so we can use that and then plug that in to find our other intercept of t. So if we put 0 in for d, that's when our distance is 0, and find out, this is really what we're finding here, is when will she get to the other side. And if you solve this by subtracting 80 and then dividing by -3, you get the t equals 26 2/3. So that's our other intercept. So we have our first intercept is at 80 on the distance axis, the y-axis. And then on the x-axis, which is at our time, we need to kind of estimate a little bit, but it's at 26 2/3. We could have also graphed this by using the equation y equals, it was minus 3t plus 80. So we could have started at 80 and then went down 3 over 1, down 3 over 1, down 3 over 1, and got the same thing. This is another example. In this one, we're given a table of arrow distance, that's the distance from the archer, and the height that the arrow goes. So we are going to create a graph, an equation, and a verbal description to go with the table. So here's our table. To graph this, first we're going to check our finite differences. So what we're going to do is take our table and we're going to find the distance between our difference between these values here, and we can see that that's a difference each time of plus 75. And then let's find these differences, because if you know the first differences are the same, then it's linear. If the second differences are the same, it's quadratic. If the ratio of the second differences is the same, then it's exponential. So those are some different patterns that we've learned before. So let's see what we've got. So this is just the second row of data, and the first differences are not the same, so it's not a linear function. But if we find the second differences, the differences between these, we see that each time it goes down 22.5. That tells us that this is a quadratic function. So we can use quadratic regression to write an equation. Now, we've done this before. You can use a graphing calculator, or you can use Desmos. We use Desmos.com to do our regression. And at Desmos.com, we would type in just like this, except we use Y1, and then we use this similar key, and then we use ax1 squared plus bx1 plus c after we enter our data into the table. And then that runs the linear or quadratic regression, and we can see if it fits the data well, and it will, and we can find that it's about 500 feet. Otherwise, it's very difficult to get this equation without using technology to do that. So here's the different translating between multiple representations. This is on your worksheet as well. If you are given a table, you can try to find whether it's linear, quadratic, exponential, use the differences of the second row of the table, or sometimes it's the second column, to determine if it's linear, quadratic, or regression. We can also graph the points as ordered pairs and look for a pattern, and you might be able to tell. And then you can run regression using Desmos.com, or if you have a TI-84, you can use that. If you are given a graph, look at the graph, of course, and tell whether it looks linear, quadratic, exponential, and so on. We can pick points off the graph and write them in a table and then interpret the table. You can also look for slope and see if it's increasing or decreasing, see if there's constant intervals and things like that to write a verbal description. If you're given an equation, you can use that to make a table of values. And you can make a graph by using, Desmos.com or TI-84, or sometimes by hand. They're easy enough sometimes by hand to do them. And if you're given a verbal description, you can usually write an equation from that. If they give you enough information, you can generate a table and then sketch a graph from the description as well. Remember that if it's linear, you can either use slope-intercept form, which is y equals mx plus b, or sometimes point-slope form is more helpful. That is y minus y1 equals m times x minus x1, where m is the slope, just like in this one, and x sub 1, y sub 1 is a point on the line. We did some of those way at the beginning of the year and in Algebra 1. First differences are constant in linear functions, and second differences are constant in quadratic functions. And then we're going to try to determine what we should have for this one. It says that a hotel manager knows that the number of rooms that guests will rent depends on the price. The hotel revenue depends on both the price and the number of rooms rented. The table shows the hotel's average nightly revenue based on room price. Use a graph and an equation to find the price that the manager should charge in order to maximize his revenue. So we use that information to make a table. And then here is the graph made from that table. And you can see it does not look linear, it's curving. It looks maybe quadratic. So if we check the differences, we can also see that it's not linear because they're not increasing by exactly the same amount each time. So then we check the second differences. So the first differences are there, and the second differences are each 400. So quadratic will fit. So now we can use Desmos.com or a graphing calculator, and we can do a quadratic regression to get the exact equation. And the exact equation is you take your value of A, B, and C, and you plug them back in to your equation, whether it's Desmos or the graphing calculator. So this equation would be y equals negative 2x squared plus 440b plus 0 for C. Oh, not b, x, sorry. And then you don't have to write plus 0. So that's the equation. And then to find the maximum point, that's what they ask about, you can either find that point using Desmos or your graphing calculator, or you could, let's see, it looks like the maximum is at 110. Yeah, that's the best way, is just to find that point there. There is other ways to find it, but we'll just go with that for now. And there's the equation. The max occurs when the hotel manager charges $110 per room. Because if he starts charging more than that, people stop coming because it's too much money. This is another type of problem using this. We have an investor buys a property for $100,000. Experts expect the property to increase in value by about 6% per year. Use a table, a graph, and an equation to predict the number of years it will take for the property to be worth more than $150,000. So it's going to increase in value 6% per year. So we can make our chart, and the first year it's going to go up 6%. The second year it's going to go up 6% of what it was already at. Now this looks somewhat linear. It's not actually linear, but it's almost looks linear. We can tell that it's not linear if you look at the differences. This one increases by 6,000. The next one increases by 6,360. The next one increases by more than that. I don't know the exact amount, but it's increasing by more than that each time. The second differences also will not be constant, but if we take our second differences and, let's see, check for a common ratio. So they're taking their amounts and dividing them from the table, and they got 1.06 for all of them. So they have a common ratio. So we'll use an exponential model, and we can use Desmos.com and use the, where is it at? Here's the Desmos regression model. Y sub 1 is similar to A times B to the X sub 1. And we find that exponential pattern does mark it, and you'll trace it along until you find 150 on the graph when y is equal to 150,000. So up here, when you get to 150, actually it's like right here, I guess, then you'll know, and it says x is 7. And we'll look at one of these on your worksheet now. All right, so here's your worksheet. Here's the same information that we just went over. And then we have some problems. There's an example as well. So on this one, it's use the data to create a table. Use the Insert Shapes tool in Word to plot the points and draw a line, or you can make your graph in Sketchpad or Desmos and copy and paste here. So here is our data, and you can use the, let me move this over a little bit, Insert Shapes in Word, and I'm just going to draw a tiny circle at 1992 and up 28. Now I don't have an exact spot of 28 there, so I'll just put it right there, right below the 30. And then I would do the same thing for 1996 and for 42. 1996 up 42. Whoops, I have to get my shape first. Insert Shapes. Insert Shapes, 42. Okay, so let's assume that we've got all of them on there, and now I need to draw a line. So I go to Insert Shapes, and I get the line tool. There it is. And then I'm going to sketch my line through the points, and this is going to appear to be linear. You'll see when you get all your data. And I extended it a little bit so I could see what the y-axis might be. Now we're going to write the equation of that line. When we write a linear equation, we might want to use the, let me make this so I can, it is a docx, okay. I wanted to draw with my pen tool and it's not letting me. Sometimes I have to convert it to get it to do that. Okay, I don't know why it wasn't working, but now it is. So we could use the y minus y sub 1 equals m times x minus x sub 1. This would be a good, the point slope form of line would be good because I have plenty of points that I could use. These are the x points, these are the y. So I'm going to put that the y is y minus 28 equals m, I need to find m still, and x minus 1992. And for m, the slope is the difference in the y values, y2 minus y1, rise over run, over x2 minus x1. So I'll take 42 minus 28 over 1996 minus 1992. So we would get 42 minus 28 is 14, and 1996 minus 1992 is 4, so this is the same as 7/2. So our slope is 7/2. So y minus 28 equals 7/2 times x minus 1992. Now if you want to write that in slope-intercept form, then we would just solve this by adding 28 to both sides. So we would get y equals 7/2 x. I need to find out what 7/2 times 1992 is. So my calculator is here. So the 1992 can be divided by 2. Whoa, I got too many 9s there. Divided by 2. Okay, that didn't make sense because it's divisible by 2. Divided by 2, and then multiply that by 7. 6972. And then I have to add the 28. So 7/2 x minus 7/2 times 1992 is the minus 6,972, and then I'd have to add 28 to that to finally get y equals 7/2 x minus, now I have to figure out what is the difference there of the 6,972, and add 28 to that is 6,944. Okay, that would be my equation of this line. Now it seems like this number is larger than it should be, so I just want to go back and see if I did something strange. No, I didn't, and here's why. Is because 1990 is right here. They're saying it's not going to go through the y-axis until this is 0, which is way, which is why this number is so crazy. Now another way of doing this is you could say, you could just use these values as after 1990. So you could use this as 0, 2, 4, 6, 8, which changes your, well, it changes a lot of things. And it would change that y-intercept to make more sense with this graph. But I was using the actual years. All right, so scrolling on down here. If we have one that does not seem to be linear, like this, to determine, we look at our first differences. So we subtract these and we see if they're constant. If they're constant, it's linear. If they're not constant, then check the second differences. So you take the differences of those and subtract those. If they're constant, then it's probably quadratic. Now we can check this at Desmos.com. So here I am at desmos.com, and I need to add this data. So I'm going to add a table. And in my table, I'm going to use the time as the X and the height as my Y values. And I just put each of these data points in. And I'm going to see if possibly this is a quadratic, which is what my instinct is, because I checked my second differences and they were constant. Also, when you see these, you might look at it and say, hey, that looks... And now they're coming down again. It went up and now they're coming down, which is another indication that it's going to be quadratic, because it increases and then it decreases the Y values. The heights went up and came down. Okay, so I'm going to make this a little bigger. Got our data. All right, so I can't see my points because the Y values are too high. So remember, click on that little wrench or whatever that thing is called. And my x-axis is fine the way it is, but my y-axis is not showing what I need it to show. I need it to go up to and past like 61, so I'll say 65. Okay, so now I can see that this does indeed go up and then come back down. So it does look quadratic. Now to do the quadratic regression, we type y sub 1. So you can just put a 1 after it, and Desmos knows that that's what you mean. And then we use that similar key on your keyboard. I can probably find it on here somewhere. Yeah, it's this key. And then we're going to go back to here. We're going to type in that this is going to be a times x sub 1 squared plus b, and you can use the letters on your keyboard too, you don't have to keep switching back and forth, times x sub 1 plus c. And this will run the regression for quadratic, and we'll see that it does fit, this red line does fit our data points very well. So let's hide this keypad. We can see that r squared is 1 exactly. So this is definitely a quadratic function. To write your quadratic function for your answer, you're going to type y equals, and then instead of a times x squared, you're going to type in what you got for a, which is, or what Desmos got for a, which is negative 4.9 x squared, and then plus, and then don't type b, type in that b is 18x, and then c is plus 45. So you take these values and plug them back into your standard form of your equation of a quadratic. And you can see that this purple line graphed right on top of the red line, which shows that it's exactly right. I'm going to copy this and then go back to our worksheet. If I can find the right worksheet here. This was 9.1. So the, oh, I'm still in pencil tool. There's my equation. I tried copying from Desmos. It didn't work exactly smoothly, but it's pretty close. And then the question says, when does the rocket reach its maximum height? I'm going to go back to Desmos. Its maximum height is right here. Desmos even put a point there for us. And that's at 1.837 seconds. It reached its maximum height of 61.531. Is this in meters or feet? Whatever it was. And the rest of your worksheet is going to be similar to that. You use Desmos to make your graphs. This one does not ask you, you don't have to show the graph, but if I did, I would take a screenshot and then just paste it in here. In the next section, you're just going to match graphs to a verbal description. And then these ones you'll be using, again, you can either use Desmos, or if it's linear, you might have an easy enough time to just graph it with the insert drawing tools in Word. And this one might be linear too. The linear ones are fine to make just using the insert shapes and then pick the right, the dots and the line tool. Or you can just do it at Desmos or Sketchpad. All right, well, thank you very much and have a great day.